Earth system earlier this week, and that's typically the kind of components of the Earth system that you want to have in your climate model if you want to project the evolution of climate over the next decades. So, of course, here what you have is atmospheric chemistry, atmospheric physics, and the water cycle here. You have the ocean on that side, physics of the ocean, geochemistry of the ocean, and you have the land here, and the cryosphere. And you see that the humans here, that kind of scheme, are represented only by their impact on atmospheric composition, CO2, but also the other greenhouse gases and aerosols. And the other big human impact here is, of course, land use, for which you have also models that are embedded in those big climate models. So that's a nice picture. The way you represent the models is not as nice. That's an example from the IPSL couple model. That's the model we use in Paris. And you see here all the components of the Earth system models. So in fact, an Earth system models is the coupling of different components, of different submodels if you want. And you have here the physical part of the system with the atmosphere, the land surface, and the ocean, and the sea ice. That's the physical kind of model you want. And on the other side, you have the biochemistry models for the atmosphere here, tropospheric and stratospheric, and for the ocean and the land surface. Basically, that's the typical class of models that are used in IPCC to project climate, carbon cycle, and atmospheric chemistry. And then on the other side, that's the model. You have the forcing, what we use as external agents of the model, and you have natural forcing, solar gravity, volcanic aerosols, and then some of the anthropogenic forcing, land use, CO2 emissions, and other gas. So that's the full picture. What we do now is, of course, some key manipulation of definitions around ESM. So when you hear about couple model, of course, the definition strongly depends on whom you speak to. When most of the time, if you speak to a climate scientist, the couple model is only the ocean atmosphere general circulation model. So that's the climate model. And those have been among the first couple models in the way we speak about them today. If you talk to marine biogeochemists, then a couple model is a couple physical biogeochemical model. And if you talk to Bopp, for example, a couple model will also be something else. So we need to be very precise when we talk here within different communities about what we mean by couple models. And in fact, when I mentioned Earth system models, in fact, what we have is the coupling of many sub-models of model components. So we mentioned the different sub-models of the coupling system. And in the case of the Earth system model that I was mentioning, that's the list of the models that I mentioned earlier. And each of these models is a huge code program with hundreds of thousands of lines, maybe millions of lines of code. So nobody is really able to know everything about all those sub-models, but you will have one specialist of each of those components working for the implementation of these components in the Earth system. And then maybe one of the points that I want to make is to build those big models, lots of lines of tools, quite very costly to run on supercomputers. But of course, those models stay quite flexible. You can use the full blown system. But you can use also only a part of the Earth system model. You can use the components or the sub-models independently. And you can use only a fraction of the Earth system model. That's what I will show now. And I will illustrate this with what we've done for the couple model intercomparison exercise for the next IPCC report. So you've seen before the entire model here. So what we do, we do a two-step approach. Basically, if you run with the atmospheric chemistry here, it costs too much to be able to run 150 years. And that's what you need to do to project climate. So what we do, in fact, is we use only a subset of the entire Earth system model with no ocean, only the atmospheric GCL and the atmospheric chemistry. And we force this model with emissions of gases, aerosols, some natural emissions, some natural forcing here. And this model, it goes very quickly to equilibrium because you don't have the ocean machinery here. And it's run only a few years every 2-3 decades. basically we create for every 2-3 decades fields of aerosols and atmospheric chemistry. So that's how we do. And then the second step, you use those fields that you've created and you run the climate couple model coupled to the carbon cycle models. That costs much less. We can do the whole transient experiment from 1850 to 2100. So when you see those big models, be aware that usually we don't run the big models. We run components of the models, we force offline some other components of the models. That's how we go. I think it's quite cool. So now, the last one I want to do, it's on the coupling between climate, the carbon cycle, and the economy. So Rashid mentioned that this morning, of course, with the Kyoto Protocol and how we can deal with emissions and concentration and climate. And I want to illustrate this with the approach that was followed in the previous IPCC report, AR4, that's IPCC 2007, and the new approach that we use now. And I will illustrate how we use this suite of models, climate models, carbon models, and even economy, integrated assessment models, and to show how we can use all those models, not together in only one big code, but separately. So in the AR4, so that's IPCC 2007, what was followed is what we call a sequential approach. So first you need the economists basically using integrated assessment models, so that's the models that Beth described this morning, that's another photo. You need them to provide concentration scenarios, emission scenarios of CO2, other greenhouse gases, aerosols, are based on pathway development scenarios. Once you have those scenarios, you can compute the relative forcing of those climate agents and climate projections. So that's basically the climate part of the IPCC. And then the third part is the impact, adaptation, and vulnerability. So you use impact models to compute the cost of some specific scenarios and some specific climate projections. So that was the approach that was used before. And in fact, by doing this, and by copying the model only that way, you miss some of the feedbacks of the system. So you have the cost of mitigation can be computed here, but the cost of impact is here. So you have different models, and sometimes different communities that don't talk to each other, so that's difficult. And so you have concentration scenarios here, and you have climate projections, but if the climate changes the way the natural things absorb carbon, you have also feedback that are not taken into account. So the new approach that is followed now in the new IPCC that will be published in 2030 is a parallel approach. So the idea was to say, we will start with some representative concentration pathways or some representative scenarios, which give basically levels of relative forcing. That's the 4 scenarios that I mentioned the second day. I'll come back to that. And then, with those relative forcing scenarios, you can compute the evolution of climate and of the carbon cycle. And with the carbon cycle here, and with the concentration pathways, you can deduce some compatible emissions that come to that. And then in parallel, you can work on emissions and socioeconomic scenarios that could match both the initial scenarios that you have for concentration and some climate and carbon cycle computations evolution. And then you can work almost at the same time with the integrated assessment models and the impact models based on the climate projections. So the example is the following. You have those 4 CO2 concentration pathways that I mentioned. That's the RCP, representative concentration pathways. That have been, so those are just 4 examples that have been used to cover the entire space with one highly mitigated scenario here that doesn't reach 450 ppm, that's the 2 degrees if you want, and one more business as usual baseline scenario, which is the RCP 8.5. So with this, plus some other aerosol chemistry components that I described earlier, we can force a climate model. And in most of the climate models now, we have also carbon cycle components. So you can have climate projections, and at the same time, you can have the CO2 fluxes to the land sink and to the ocean sink based on the CO2 that you impose and based on the climate. So you have this climate carbon right? So that's an example. You have the atmospheric CO2, the same 4 scenarios here. that's the ocean carbon uptake computed by the oceanic carbon cycle component of the ATS system model. And that's the non-carbon uptake. So in that case, the ocean takes up carbon because you have more and more CO2 in the atmosphere, but you have also the effect of warming, reduction of the carbon uptake. So you have those four scenarios, and you have the carbon uptake. And here on the bottom, you have the land uptake of carbon due to increasing atmospheric CO2, due to changing climate, but also due to land-use scenarios. So all this is embedded and computed here by this land carbon model. All those models are spatially explicit on the same grid that the climate model. And once you know the atmospheric CO2, and if you know the oceanic carbon uptake and the non-carbon uptake, the missing piece in the budget here is the anthropogenic emissions by fossil fuel combustion. So you can just do a very simple calculation. The increase in CO2 is due to some emissions minus the oceanic carbon uptake and the non-carbon uptake. So by using this model, you can compute what we call the compatible emissions. So that's the emissions your model would like to see if you wanted to follow the concentration pass rate that I mentioned earlier. So you see that in the, so we check that on the historical period we have emissions that are close to the one that, that's the case. In 2000 you have emissions close to 8 petagram of carbon, which is the amount of carbon we put today in the atmosphere. And then for the 4 different scenarios, you have what we call here those compatible or permissible emissions. And for example, in the RCP 8.5, the climate carbon model tells you that you could emit up to maybe 28 petagram of carbon per year to follow this concentration pass rate. What's interesting also is that in the RCP 2.6, that reaches 4.5 and then decreases, 450 and then decreases. You see that our model, and the other models also, tells you that you need a negative permissible emissions to follow this CO2 concentration pass rate. So you need basically to absorb carbon anthropogenically instead of emitting carbon to follow the pass rate that was imposed to your climate and carbon. So that's the cumulative compatible emissions, so just the integral of the previous curves for the 4 scenarios, and you see the negative emissions here because you need to reduce the cumulative emissions in case of RCP 2.6. And so basically what we do here is what I was mentioning here. With these models and those scenarios here, we compute the compatible emissions, and then we pass them to the economists that run integrated assessment models. And then they can propose basically economic pass rates to meet the compatible or the permissible emissions that we compute with the climate carbon models. So that's another example of the way we couple models. Here, climate carbon full couple models, an integrated assessment models, and some scenarios to force both of the models. So with those compatible emissions, and that's an exercise we did in a French project using the integrated assessment model that is called IMBER ClimEco3. And here they compute the GDP loss compared to some baseline scenario in case of those 4 RCP scenarios. So in RCP 2.6, you reduce a lot the emissions, then you have the outcome here is that this integrated assessment model will tell you that you will have a GDP loss of maybe 20% in 2035. And then you can play with these integrated assessment models and play different games or scenarios. You have no, in that case, so for the same scenarios, so the same emissions, if you don't have any carbon capture and storage, then it's much more complicated to reach the target, and so you have a larger decrease in GDP if you have no nuclear power or only weak biomass, or if you have only a weak energetic intensity that gives you different ranges here. Okay, so I stop here. Those are not about fisheries, but it's also, I think it's about coupling, and it shows you when you play with those different models, even if they are very complicated, you can have them talk to each other with very simple quantities. Here, basically, you have 2 complicated systems, the climate carbon model and the integrated assessment models. And you just exchange those permissible emissions that are global emissions. And that's a way to have all those effects into account and different feedbacks, some of the feedbacks in the system. Stop here, maybe.
Can I make a quick comment? Can you go back to the one that showed? Yeah. my talk, I had shown the long-term CO2 where you increase CO2 and methane, but the temperature is still catching up. So it is very important to focus on adaptation because even if we cut all the emissions to zero, the amount of oil we put in is going to make a lot of impact in the coming years, especially for developing the world.
I agree, but then, I agree, of course. Even if it's density 2.6, we have global warming, we have large changes. But the differences at the end of the century between this scenario and this scenario are huge.
Yeah.
So we won't be able to go, adaptation will be very different if we do mitigate or if we don't mitigate. So.
Yeah, and my comment is not to say that we don't need adaptation. The thing that led me to this thinking, in March this year, there was a meeting in Taiwan, right? And APEC group of nations, talking about extreme weather and the consequences of that. Because Taiwan suffered a big one, 2010, it's unbelievable tragedy. So they organized this. Then all the government officials were talking about adaptation, almost forgetting about mitigation. That's the problem. It's just overstressing adaptation. Because look, there are two things there. If we just keep pumping and this thing gets worse, even the strong countries, they find it difficult to adapt because there's more repairs. Right? That's one thing. And then for the developing countries, adaptation is really difficult. Right? If you are poor, your capacity to adapt is really weak. So you better fight for mitigation anyhow, because you see what I'm saying? I could talk about this forever. One guy was saying in Amsterdam that don't worry about climate change because if it comes, all you need to do is just take your bag and just move to another place. And I was sitting there smiling. This guy has never applied for visa from a developing country to go elsewhere. He'll never say that. So that is not is a balance.
Mitigation has two aspects. One, such as getting ready. We know nothing about the impacts of trying to sequester carbon. That has to be done very carefully. Secondly, the basic adaptation techniques of not cutting down forests or using agroforestry and other things are being ignored in a rush to develop some planetary solutions. So I think mitigation that has to be done very carefully.
Okay, basically I'll sort of pick up where Laurel left off. So basically what he's talked about and what happens in coupled models is you have to cover enormous ranges of scale. So in somewhere like Australia, obviously, or anywhere in the world, you've got the animals happening on the meter scale in their interactions, but the physics end of the world is happening potentially at basin scales. And why would you need all of those things in a model that even if you're just thinking about how to manage a single reef in Australia, for instance? That's because the shelf properties, the actual thing that's happening on the reef, it spans like, 10 orders of magnitude, 12 orders of magnitude there from the small scale fish interactions up to how the reef system itself is physically affected. But even the management guys, the guys who have to decide if they're closing a reef or putting in a fish minimum size limit so you don't catch too many small fish, the area that they've got to worry about covers 2 to 3 orders of magnitude. So that's why so many scales end up in these big coupled or even small coupled models, because there's so many scales involved in the day-to-day processes that are happening. So those coupling things can happen sort of inside the model, so they're not explicitly look like they're coupled, but it's actually the same thought processes that have to happen. So for instance, there's lots of different ways of modelling the world. If we think about bringing human into it, ideally you need social, economic, and biophysical, whether it's a simple qualitative model, a model sort of intermediate complexity to play with, a model that focuses only on one sector, like a fisheries model, or these more complicated models that start to shuttle ideas around where you actually do have feedbacks amongst more of the system. So you've got to think about which ones to include, what sources of delay do you have, and then ultimately what kind of coupling you want. So originally, pretty much every model in the world has started by coupling in one direction because that's easy. But a lot of the feedbacks, a lot of the critical behaviour that happen is only turns up when you get the two-way couple. And that's as computing power and skill and human ingenuity is moving forward, we're getting more and more of that happening. So that's the part that I'll try to focus on. So if we think about the whole of a marine system, these are all the different parts that we have to actually think about whether we need to couple them together and then how we do that. So if we just go on a brief tour of Beth's career, when I first started as a baby modeler, the physics end of the world didn't talk to the fish end of the world, they were separate. And people would say, well, that's not good enough. We probably need to have more than just phytoplankton in a physical model, so that adds zooplankton. And the fish guys would go, well, the fish might need to eat something or live on something, so they'll add one more group there. And then I came along and said, well, my supervisor suggested I should say, right, what happens if we tied everything together and we get different fisheries questions? Ironically, I never got around to answering that question. I got so sidetracked with how you tied everything together. Since that time, over the last 15 years, there's been lots of different ways about tying these things together. You can either have the same degree of detail the whole way through, you can focus in the middle and sort of just paint in the things at either end. You can use the rhomboid approach and go for a lot of detail at certain steps down the chain but have thin links between them. But what's happening more and more is these hybrid models at the other end, where you use the best way of representing each part of the system and then figure out how to get those different things to talk together in a big Franken model, so that it's all bolted together. Now, one way you can do that is to have like a translator sitting in the middle. So if you think about the UN, the whole thing would collapse if there wasn't those people who could speak as fast as they can think in a different language. So the language is coming in one ear and say French and coming out their mouth in English. The UN couldn't communicate in the General Assembly without that translator happening. The same thing can be used to couple models together. So you don't have to have the overhead of trying to take a Laurent's model and say, look, you have to have my equations coded in, or you have to do things like I do, or vice versa. We can have a translator sit in the middle who knows how to speak the two languages. So information comes out of Atlantis, gets translated into French by the broker, and gets passed to Laurent's physical model, for instance. Well, it wouldn't be French, it would be what, C4 trade or whatever. One of the complicating factors in doing that is think about how you handle space. Because the models have grown up differently, they won't handle space and time in the same way. So two of the most common ways of treating space are, the most common way is just to do a homogeneous grid everywhere. The other way is to try and break up the world, not to think necessarily in a regular grid, but to try to match the detail of the grid to where the detail of the action happens. I wasn't smart, I didn't think this up because I'm some kind of super genius. It was because when I started modelling, we couldn't fit the area I wanted literally as a matrix onto the size of the computer chip. It was too big. We'd have to keep swapping things in and out, it would be too slow. So I had to think about how to reduce the size of that matrix by having less boxes. So I sat down and thought about when you're sampling data, or actually when you look at an animal's behaviour or the physical properties like fronts, they happen in very concentrated areas, and other areas are quite, you can get away with a simpler characterization. And that's what led to this kind of box model approach that I use, but it was actually commonly used a lot more by the broader community back then. The physics guys have been better than ecologists at getting super big computers, so they've been able to go over to using this. The ecologists still do this sort of small computers. But regardless of how you model it, you have to be aware of the kind of artifacts that can chuck up. So this is an example from a big global model, and you can see with the red bits, that's where the estimated sea surface temperature was wrong. It was basically as much as 6 degrees wrong. The reason behind that was that the resolution and the kinds of physics they had in upwelling zones, where the physical properties changed quite rapidly and other processes are dominating, didn't match what was actually happening in reality. So one way to solve that was to use a finer grid, for instance, and bring in slightly different formulations. So in Australia, for instance, we went from a prediction that was really quite smooth and smeared to one that captured all the eddies that actually drive production. So you can imagine that if you're a fisheries manager trying to make decisions, you'd actually make very different decisions, particularly along the coast of eastern Australia, around here, based on whether you were using a smooth model or this model with eddies. And tuners love to sit on the edge. tropical tuna in Australia sit there, and the southern tuna sits there. So if you've got your management and you're basing it, trying to be proactive and put management, spatial management in place, and you put it here, and they're actually all up here, you're going to have caught yourself a problem. When they adjusted the physics though, you can see that the biases aren't all gone, but it solved quite a lot of the problem. And there's a few different ways that that can be done. So for instance, you don't have to use a regular grid everywhere. You can even on those big climate models sort of zoom in and out as you need. Or you can go a different way and say actually in those zones where it's processes on a different scale that are driving the system, zoom your scale down by embedding a fine scale mesh inside that big grid. On the temporal resolution front, most models that we would think of, like what we're doing in NetLogo, everything in the model steps together on a constant heartbeat. Everybody has the same sense of time. There is a little bit of a trick in ecology where animals that grow slowly will do one big step, and animals that grow fast will do lots of little steps till they've added up to that one big step and then go to the next one. The reason they do that is just for numerical stability. So you have plankton that go very fast and fish that go once. You don't want to calculate fish on a second time step, it takes everything too long and they don't really act that way. But some of the plankton, you have a couple of minutes or a couple of hours for a plankton can be a long time. The other way to do it though is, what you've heard me talk about a little already, is you don't use the same time step for everything. So the bottom one is the kind of time steps I use in a model that's agent based where the action of the animal or the agent dictates its time step. So for instance, a regional economy will go off once every 6 months. A fishing boat will make its decisions on a daily basis. And a fish will make its decisions on a minute-by-minute basis while it's awake, but longer times when it's asleep. Or teenagers will spend 12 hours asleep, so you might as well save yourself some computational time by not ticking them. But then if they're running away from the police, then they want a faster time step so they can play out the chase. You do need an underlying heartbeat though, so things don't end up too far apart. We're just playing with science fiction because half the animals are in the future. When you start to be able to deal with those kind of scale problems though, you can start to couple things, really couple things together. So sometimes that coupling is by putting it all together in the same model and having the translation happen in that one piece of software. Other times you tie the software together. So this is an example of where the temperature has been tied to phytoplankton in a nutrient field, so that you can see the evolution of all things together. And most of you would actually be quite aware of that, but you can take that process much higher up the trophic chain. So a French group has actually done this, where they had a climate model, drive a primary production model, drive a feed layer, so they didn't actually species resolve the feed, it was a size-based model, a different model again. Then they had a larval advection model, so a different model again. And finally they had the adult tuna, so they actually coupled this whole chain of models together with feedbacks to be able to cover that in what can be a global span simulation of the tuna. Just like you've got your physical and your temporal constraints on the resolutions and the processes, you've got to think about the same is true for any living part of the system. So we heard earlier in the week about some of the ways that you have to think about when you're putting your trophic web together. When do you need to split the animals apart? When do you need to resolve the animals, and when do you lump them together? There's actually a whole bunch of rules about when it works and when it doesn't work. So that's something we're quite comfortable with now, just like we are on the physics side. And you've got to be aware of the vampires in the basement. Ultimately, regardless of how you're putting your models together in space or time or processes, you need to allow for alternative stable states. One of the biggest mistakes is to over-hardwire your model, to lock in behaviours that you've seen that must be there. One of the best tests of a good model is to see if it can produce that behaviour rather than requiring a behaviour. Because then you have a test to see whether you may actually have the process-based model. So they've been now doing this to tie ecosystem models in the whole big whole food web sense to global climate models. For instance, in the United States, they take the climate model, they've got an embedded hydrodynamics ROMS model. Inside that hydrodynamics ROMS model, they've now linked in